So this is the problem of radial inflow. The data given in this is inlet velocity is 45 meter per second, angle of jet at inlet alpha 25, angle of vane at inlet 35, angle of vane at outlet 25, and it is mentioned that velocity of flow at outlet is 8. Velocity of flow at outlet. So this is outlet velocity triangle. This particular vector is velocity of a jet. The component in this direction, radial direction, is given to be 8 meter per second. That is what is the data given. Then radius at inlet is 50 centimeter. Radius at outlet is 30 centimeter. So what we can write is inner radius, not inner radius, radius at outlet is 0.3 meters. So you can see here there is an inlet, there is an outlet. Inlet radius is more, outlet radius is less. So R1 becomes 0.5, that is radius at inlet. Radius at outlet is 0.3. So this particular wording is not proper. Actually, radius at outlet, radius at inlet is proper. Now work done per unit weight in radial inflow case is VW1 U1 plus VW2 U2 by G. Now with the data given, I can draw the inlet velocity triangle. So here 45, 25, this 35 is given. Outlet velocity triangle, the phi angle of vane, in the sense VR2 is making an angle of 25. We don't know about beta, but velocity of flow, that is this vertical distance, is given to be 8 meter per second. Now we'll have to evaluate all these parameters. Let us see. So here I have analyzed inlet velocity triangle. These calculations are numbered 1, 2, 3. That is order in which you can analyze. So first step is VW1. What is VW1? It is this total horizontal distance, that is component of V in the direction of U. So VW1 becomes 45 cos 25, that is 40.78. This is calculated. Now step number 2 over here. So this side is calculated. Because 45 and 25 is known, I can calculate this. 45 sin 25, that is 19.01 meter per second. That is known. Now step number 3, what I have done is 19.01 can also be written as VR1 sin 35. Because 35 is given, VR1 is this, VR1 sin 35 is 19.01. So hence I will be able to calculate VR1 as 33.16. Now step number 4, the moment I know VR1, I can calculate this distance, that is VR1 cos 35 equal to 27.16. I know the total distance, I will subtract this. So step number 5, wherein I will be getting this U1 is equal to this total distance 40.78 minus 27.16, that is 13.62 meter per second would be U1. But I know the relation U1 is equal to R1 omega. R1, that is radius at inlet, is 0.5. So I'll be able to get omega, that is 27.25 radians per second. Now once I know omega and then I know R2 also, I can calculate U2. So U2, velocity of the vane at the outlet, is R2 omega, it's 8.174 meter per second. Now This is outlet velocity triangle. This was the rough sketch put in the beginning. So what is given here is VR2 is making an angle of phi 25 degrees. So this is U2 and this becomes V2. This V2 has got a vertical component as 8. That is what is the data given. Velocity of flow is given to be 8. What we need is velocity of whirl, VW2. Now how to go ahead, I have redrawn the diagram. So step number 1, I know VF2, so VR2 sine 25. In this triangle, if you look at this side, which is 8 is VR2 sine 25 equal to 8 given. So VR2 is calculated as 18.93. So here there is no assumption like VR1 equal to VR2, right? You have to calculate VR2. Now VR2 is calculated. Now step number 2, VR2 cos phi, that is VR2 is known, angle is known, that's why I'll be able to calculate this whole distance. VR2 cos phi is 17.16. This whole thing is 17.16. U2 is already calculated, so VW2 can be calculated. So step 3, VW2 is 17.16 minus 8.17, that is 9 meter per second. So here we have calculated VW2, VW1. Now calculation of efficiency or work done. So here what is asked is work done per Newton of water or per weight of water. The expression is this. I'll just substitute all the values properly and then calculate. Here plus or minus, but plus sign is used because you know that beta is less than 90 degrees. So work done becomes 64.1 meters of water. Okay, thank you.